So we have been looking at solutions where you can determine the concentration of hydronium ions to determine whether your solution is acidic or basic. When we do these calculations using our KW formula, we're using hydronium ion concentrations where we're having these exponents in it. That makes the math a little bit tricky. So there was a mathematician who came up with a formula called pH, and most people are familiar with pH, telling you if you have a solution that's an acid or a base. So the formula here is basically based on powers of 10, is the logarithmic system. It's much easier to do some calculations and then give a value of a pH whether your solution is an acid or base. For example, if we use this formula, pH is equal to the negative log of hydronium ion concentration, we would plug in the negative log, and then our hydronium ion concentration is 4.56 times 10 to the negative 9th molarity. If you plug that into your calculator, you would find out that the pH here is equal to 8.34. So that's a number that's much easier to use. So this guy is actually using a pH meter where you can determine the pH of a solution, and that will basically, it monitors the amount of ions in your solution and does a conversion into the pH scale to give you these numbers. So we're going to do some calculations using pH. pH I also like to think of as the power of the hydrogen ion, or we can say hydronium ion. So that is standing for the H here, pH, power of hydronium. To calculate pH, we just said the formula for pH is equal to the negative log of your hydronium ion concentration. This is a formula I do want you to remember, but we do have a shortcut way that we can do our math instead of using your calculator and plugging in log. If the number in front of the exponent is a 1, you can just take the exponent and then make the exponent to a positive sign, and that gives you your pH. So in this example, we have 1 times 10 to the negative 10th, 10 to the negative 3rd. The exponent is negative 3. We make that a positive sign. The pH of my solution is just 3 without having to use the calculator. If you want to, you can go ahead and plug that into your calculator. The pH scale goes from 0 to 14. And any solution that has the same amount of hydronium ions as hydroxide ions, remember that concentration would be 1.0 times 10 to the negative 7th for either one of those if it's neutral. And again, the shortcut way I said where we can determine its pH is just taking that exponent. So the pH of a neutral solution would just be 7. The negative exponent of 7, we make it a positive. So on our pH scale, anything at a pH of 7 is a neutral solution, again meaning the hydronium and hydroxide ion concentrations are equal to each other. Now anything with a pH less than 7 is acidic. And again, acidic we said means more hydronium ions than hydroxide ion concentrations. But the pH scale, again, we're using numbers that are a little bit easier than the exponents. So we just say anything with a pH less than 7 is acidic. Anything with a pH greater than 7 is basic. And again, basic means more hydroxide ions than hydronium ions. Okay, here's my pH scale again. pH in the center at 7 is neutral. Also, this one is showing you your concentration of hydronium ion here. Hydrogen ion or hydronium is 1 times 10 to the negative 7th. Anything with a pH greater than 7 is basic. And again, we can look at our concentrations of hydronium ions here are going to be very small. Anything with a pH less than 7 is an acid, and we have a higher concentration of hydronium ions. Tomato juice has a hydronium ion concentration of 1 times 10 to the negative 4th molarity. What is the pH? So again, we could use our formula. pH is equal to negative log of the hydronium ion concentration and plug that in. Or we can just take our exponent, makes our math really easy to do, make it a positive side, and our pH is 4. So tomato juice, because the pH is less than 7, means it is acidic. The hydroxide ion concentration of soap is 1 times 10 to the negative fifth molarity. What is the pH? So pH, again, is the power of your hydronium ion concentration. We are not given our hydronium ion concentration, but our hydroxide. So we need to solve for hydroxide ion concentration. Sometimes people make a mistake and they may say the pH is equal to 5. But we can't do that because that would be for hydroxide. There is something that's called pOH. Okay, pOH is the power of the hydroxide ion concentration. So that pOH, you could take the exponent and your pOH would be 5. But we're looking for pH, hydronium ion concentration, so we can solve for that using our formula. Kw is equal to hydronium times hydroxide ion concentration. Kw is 1 times 10 to the negative 14th. Is equal to our hydronium ion concentration, which is what we're trying to solve for. Hydroxide is given of 1.0 times 10 to the negative fifth. So we can solve for hydronium by dividing both sides times 1 times 10 to the negative fifth. And then we can get hydronium ion concentration by itself. And then we have a negative 14 minus a negative 5. Gives me 1.0 times 10 to the negative 9th. So my pH is, again, we can just take my exponent and make it positive. pH is 9. Now there is a shortcut way you could do this. Our pH scale goes from 0 to 14, with 7 in the center being neutral. So whatever value I have for pH and pOH, total, it has to be 14 when I add those two numbers up together. So pH plus pOH is equal to 14. So if I wanted to solve for pOH in this problem and just say 5 using the exponent, I could say pH is equal to 5, pH plus 5 is equal to 14. And then I could solve for pH by saying 14 minus 5 is equal to 9. So that's kind of a shortcut way that you can get to the pH instead of using the Kw formula. Either one is fine to do. And also realize our pH is 9, so it's greater than 7. That means my solution is base. So soaps are basic. If you are given a hydronium ion concentration where you do not have a 1 written here, so for example this one, 1 times 10 to the negative 9th, we can just take the exponent and say pH is equal to 9. If we don't have a 1 here, for example in this one below we have 6, then we have to use our calculator and use that log formula. pH is equal to the negative log of hydronium ion concentration. So we would just plug in. So in this example we're asking for the pH when our solution has a hydronium ion concentration of 6 times 10 to the negative 9th. So we can just plug in. The hydronium ion concentration is 6.0 times 10 to the negative 9th. And then you would plug in your calculator negative log times, you can put parentheses around your value for hydronium ion concentration, and you should get a pH value on your calculator that will tell you it is 8.22. If you didn't have the negative sign here and you just did the log of the number, you would get a negative 8.22, so that's why the negative is here, and negative times negative gives me a positive. So this solution, I might ask you, is it an acid or a base? Again, the pH is greater than 7, so in this example, we have a basic solution. The hydronium ion concentration of blood is 4 times 10 to the negative 8th molarity. What is the pH? So again, we don't have a 1 here, so our pH is just not 8. We have to use our formula. The negative log of hydronium ion concentration is what our pH is equal to. So then we just plug in to our formula. We're given hydronium ion concentration of 4 times 10 to the negative 8th molarity. And when we plug that in to our calculator, we end up with a pH of 7.4. The normal blood pH range is 7.35 to 7.45. So this person's blood is within the acceptable range, so they would be fine. Sometimes though, however, people's blood pH might be too low or too high. If your blood pH is below 7.30, it's a condition that is called acidosis. And some of the symptoms of this may be if you feel dizzy or faint. If you faint, it might be caused from acidosis. And some of the things that may cause you to have these symptoms of acidosis is if anyone's ever fasted, maybe for religious reasons, or if you're dieting, you might feel lightheaded to the point that you might actually faint. What happens with fasting is that your body is burning its own fat, creating acidic components that get in the blood, causing it to become a lower pH. Or heavy exercise. If you play soccer or maybe you run track, you're doing heavy exercise that produces lactic acid. That's also going to lower your blood pH. Or hypoventilation, and that's when you're not breathing in enough oxygen. That could be maybe your windpipe was obstructed, or if you're holding your breath, maybe you're underwater swimming. If you have not enough oxygen, it causes an increase of carbon dioxide in your blood, which decreases the pH of your blood. If your blood pH is greater than 7.45, it's a condition that's called alkalosis. Some of the symptoms are if you're dizzy, if you have muscle cramps, or if you go into convulsions. And this could be caused by hyperventilation. And this is when you have rapid, heavy breathing. And this could result from fever or infection or taking drugs, or maybe someone who's just hysterical and they're breathing really hard. So what happens here when you're hyperventilating is you're losing too much CO2. So you have an increased amount of oxygen in your blood, and that increases the blood level. So alkaline is another term for a solution that is basic. That's where the term alkalosis comes from. Acidosis, again, is, we said an acid was a pH that's lower than 7. Alkalosis is when your pH is going to be higher or greater than 7.45. There are different ways we can test the pH of our solution. The first example we have here is a pH meter, which is A down below. And what a pH meter does is it actually measures the concentration of hydronium ions you have in solution. And because those are ionic particles, that we can actually convert the number of ions you create into the pH scale. And actually just print out, what your pH would be of your solution. So you basically, in this one, you just put a probe into your solution. You have a meter that does this conversion of the electrical particles that are being created into the pH scale. Another way we can check pH is using pH paper. And that's in this picture right here. And this is something that you will do in the laboratory. So pH paper, it has color indicator in it that changes color depending if your solution is acid or basic. So we have a scale on the side of our bottle here, of our container, that has different colors that you would match your paper up. So you would take your piece of paper, you would dip it in a solution, the paper would change colors, and you would compare it to the scale. And you'll see that in the experiment we do on pH and buffers. Another way you could do it is creating your own color indicator, and you could actually do this at home, is you can take purple cabbage and boil it in water, and you're going to get this purple solution here. And purple cabbage has a natural color indicator in it, meaning that a color indicator is something that changes pH or changes color depending on the pH of your solution. So here we have these test tubes that are showing you with cabbage juice, depending on what the pH is, how the color changes. So this would be a low pH. The first one down here, this hot pink one, would be something that's acid. And then we come across here, depending on the pH of your solution, the ones at the very far end over here are the more basic ones. So you can create your own color indicator scale using cabbage juice and determine the acids and the bases, and you could test an unknown compound here and then determine if it's an acid or base using the scale that you created. So here we have some compounds in our everyday life, and we have our pH scale that tells us if we have, an acid or a base. So we can start up at the top here and look at some different compounds, and these might be things you want to try at home as well to determine pH. You can use that cabbage juice as a color indicator. So we can look up here, we have lemon juice, pH of 2.2, so that is going to be, obviously pretty acidic. Carbonated beverages like sodas here, pH of 3. We have oranges, 3.5. Apple juice, we looked at tomato juice, was a low pH. Coffee has also got a low pH in it. So all acidic compounds. We can look at water. Pure water, we saw, is a neutral compound, so its pH is 7. Different soaps we saw were basic. So here's a detergent, pH is around 8 to 9. We have ammonia, which is in Windex, pH around 11. Bleach, so a lot of your cleaning products. And then Drano down here at the end contains lye, sodium hydroxide. That has a very high pH, making it basic. So you do want to be careful when you're using a lot of these cleaning products that you wear gloves, because they're very strong bases that those could actually, irritate your skin. Here's just another slide, again, to show some substances in our everyday life, whether they're acidic or basic. So again, we have our acids down here, and then we have the compounds that are basic with the higher pH down at the bottom. And here again, we have that sodium hydroxide solution when it's just 4% sodium hydroxide mixed in water, gives you a pH of 14. That's pretty high. That's a very basic solution. Okay. Buffers, I want you to understand more of the definition of what a buffer is. We're not going to be doing calculations with buffers that you might see in your textbook. So buffers are basically solutions that are resistant to pH change. Meaning I have a solution that contains a buffer. I can add an acid, a strong acid, or a strong base to it, and the pH is not going to change very much. So you can think about in your body you have buffers, and you might drink a soda that has a low pH, or lemonade with a low pH because of the lemon juice in it. You have these acidic substances, and we're not getting sick by doing that because our body has buffers in it that help us resist these drastic pH changes. So a buffer is actually made of equal quantities of a weak acid and its conjugate weak base. So we'll look at an example of one of those in our body in just a moment. So buffers, basically what they do is they neutralize whether you're adding a strong acid or a strong base. Hydronium ions would be for our strong acids. Hydroxides would be our strong bases. If you add it to the solution, it neutralizes it. That's why our pH does not change very much. So primarily no definition is a buffer substance. I can add an acid or base and the pH doesn't change. In this example, we're going to be looking at adding a strong acid or a strong base to water and see how the pH is affected. And then we're going to compare it to a solution that is a buffered solution when you add a strong acid or a strong base and see how the pH changes. So in the first example here, I've got my beaker of water. I have the pH of my solution of water is neutral. It's a little hard to see the slide here. And I'm going to add hydronium ions, which represent my acid to it. So this could be a strong acid like hydrochloric acid. And what happens when I do that? My pH is going to drop. Okay, so my pH drops from 7 to 4. So there's a big pH change by adding just a little bit of acid to water. And if I have a base represented by my hydroxide ions here and I add it to water, my pH is going to increase. So this may go up to 10.5. So there's a big increase here in water. If I have a solution that contains a buffer in it and I add an acid to it, again, my buffer solution is about 7, and I add the acid to it, my pH is going to change slightly, but compared if I'm adding the same amount as I did in my water of acid, the pH is only going from 7 to 6.9. There's not a huge jump because again, our buffer system is going to neutralize those excess hydronium ions added to it because it's got a weak base in it. And then if I add hydroxide ions, my solution with a buffered system, the pH is going to go up slightly, but only to 7.1. So this example is just trying to illustrate how a buffer system, your solution is not going to change very much when you add an acid or base. And again, we have buffers in our body. And you'll be doing a very similar experiment to this in lab. We do an experiment on pH and buffers, and you'll be adding a strong acid and a strong base to a water solution and a buffered solution. A phosphate buffer system is what we have in our bodies that can help us regulate our pH. The phosphate buffer system is made of a weak acid and its conjugate weak base. because again, that's what our buffer is. It's a weak acid and its conjugate weak base. And just to illustrate again how this happens is here we have our acid. We're adding hydroxide, which represents our base. So it's our weak acid. And we can look at its conjugate acid and conjugate base. So if we have an acid, this would be its conjugate base, because the hydrogen again is being donated from the acid to the base. We're left with only one hydrogen now, and then the PO4 part stays the same. We have a -1. We're taking away a +1, so it becomes more negative. And then the base, the hydroxide ion, accepted that hydrogen ion and became H2O. So we have two hydrogens. It was a -1. We added a +1, so that's neutral. And then in our system, again, what we've created here, my conjugate base, is what we have in our original system. So if we added a strong acid, represented by H3O, again, we can look at our conjugate acid, conjugate base. So in this case, this is the acid. The acid is donating the hydrogen ion to the base. And when it donates that, the acid, its conjugate base, this one was conjugate acid up at the top. I didn't label that. The conjugate base is your water, because it's what it becomes after it loses. We had H3O, we lose a hydrogen, now we have H2O, we lose a positive sign, we get a neutral compound. The HPO4 2- is the one that's gaining that hydrogen, so we now have two hydrogens. It's a -2. We add +1, we get the -1. So this is again showing, similar in the previous slide down here at the bottom, that our buffer system has a pH of about 7.21. So we're comparing here, if I have just water, I add a strong acid, hydrochloric acid, my pH of water is 7. When I add hydrochloric acid, and again, depends on how much I add, my pH drops to 1. If I have my phosphate buffer system, and I add an equal amount of hydrochloric acid as I did to the water, the pH goes from 7.21, very slight change, to 7.12. Again, if I use a base, a strong base, NaOH is one of our strong bases. If I have water, I add sodium hydroxide. My pH goes from 7 being neutral up to a high pH. My phosphate buffer system, when I add sodium hydroxide to it, pH goes from 7.21, goes up slightly to 7.30. So again, this is just illustrating our buffer system, how it helps us maintain the pH, and just changes slightly when I add a strong acid or a strong base to it. So let's do a learning check to finish out our chapter on acid and bases. So I have a number of solutions here, and I want you to determine if they are acidic, basic, or neutral. So we'll put the number in the slot that helps us define that. So we have hydrochloric acid has a pH of 1.5. So that one should be acidic because our pH is less than 7. Remember, hydrochloric acid is that acid in your stomach that helps you digest food. Pancreatic fluid, you have a hydronium ion concentration of 1 × 10⁻⁸. So again, we can quickly determine the pH of our solution is just the exponent is 8. So our pH here is 8, so it's greater than 7, so we have a base. The next one we have Sprite soft drink. Its pH is 3. So again, less than 7, we can say that is an acid. If we have a solution that has a pH of 7, that's our definition of what's neutral. So I'm going to put a 3 in there. Now we have hydroxide ion concentration is equal to 3 × 10⁻⁻10 molarity. So we could go ahead and plug that into our calculator and do POH is equal to the negative log. Again, this is hydronium ion concentration. And we could solve for that, and we would get POH is equal to 10.477. We could solve for pH. pH is going to be equal to 14 minus 10.477, and our pH is equal to 3.523. So again, our pH is less than 7, so we have an acid. Now, if you didn't want to go through, and this is just a quick check here, you could also look at your concentration of hydroxide ions and compare that to hydronium ions. So if I have more hydronium ions, then my solution is going to be acidic. So remember, hydroxide ion concentration, 3 times 10 to the negative 10th is a very small number. So that means hydronium ions has to be more. So in this example, we could just say hydronium ion concentration is greater than hydroxide ion concentration. So we also know that that's an acid. The one at the bottom, again, we can go through and use our formula. We're given hydronium ion concentration, so we can calculate pH is equal to the negative log of our hydronium, which is 5 times 10 to the negative 12th. If we wanted to calculate this all out, and we would get the pH is equal to 11.3, which tells us our solution is basic because it's greater than 7. Or again, we can look at this number and say, oh, 10 to the negative 12, that's a very small number here of hydronium ion concentration. So that means we have to have more hydroxide ion concentration in this example than we have hydronium ions. And if we have more hydroxide ions, then we have a base. So hopefully that will help as a recap on our acid and bases, being able to classify solutions.